Hello everyone. The purpose of this video is to introduce solutions. So we're going to start with the dissolution process, and before you start this you may want to go back and review intermolecular forces. We will be using the intermolecular forces throughout this video and future videos as well. So keep in mind that ion dipole attractions, we're going to talk about those more in this chapter. And those are going to occur between an ion and a polar molecule. You also have dipole-dipole attractions that are between polar molecules, and you have especially strong dipole-dipole attractions called hydrogen bonds. Remember, those have to be a hydrogen directly bonded to a nitrogen, an oxygen, or a fluorine, and that hydrogen has to be directly bonded. Okay, we also have dispersion forces. Those are going to be present throughout all types of molecules, and it's very important to remember the strength of each of these interactions. So of course, dispersion forces are going to be your weakest force. Ion dipole is the strongest, and hydrogen bonding is a stronger version of the dipole-dipole attractions. Okay, so solutions, as you probably know, are homogeneous mixtures. And remember, when you hear the word homogeneous, that just means uniform throughout, right? And this is in contrast to heterogeneous mixtures that are considered to be more chunky or not evenly mixed. So a solution is going to be composed of one or more solutes as well as a solvent. So the solvent is going to be the substance that is present in the largest amount, and everything else is going to be dissolved in that solvent. So solutions can be made of all three types of physical states. You can have gas solutes dissolve in liquid solvents. You could have liquid solutes dissolve in gas solvents in any combination, right? But we're going to define the solution based on the solvent. So when we say we have a solid solution, that typically means that the solvent is a solid and the solutes could be any combination of gas, liquid, or solid. So an example of a solid solution would be metal alloys. This would be two or more metals. You can also have gas solutions like air, and air is going to be composed mostly of gases, but you also have some water vapor in there as well, so you do have some liquids. And then liquid solution, that's what we're going to focus on for the majority of this video and future videos. And keep in mind that most of the time water is going to be the solvent, okay? And that's when we talk about what we call aqueous solutions. So keep in mind that when you're looking at balanced chemical equations, when you see that parentheses AQ, right, that just means that that solid has been dissolved in water. Okay, so in this example, we have sucrose that is being dissolved in water, and that's what we call a covalent compound. So it's not going to dissociate, but it will dissolve. Now, potassium dichromate, the second example here, that is an ionic compound. And so when ionic compounds dissolve in water, they also dissociate. And remember, dissociate means to break apart into its separate ions. Right. So when that potassium dichromate dissolves in water, it's going to form separate ions of potassium and dichromate. So just to summarize solution characteristics, the solutions are going to be considered homogeneous, which just means that they are uniform in their composition. The physical state of the solution is going to be defined by that of the solvent. And then the components of a solution are a mixture of separated solute particles that are going to be surrounded by the solvent species. And we'll see several pictures as we continue on in this video. The solute cannot settle out or separate from that solvent, and the composition of the solution or the concentrations, they can vary, right? So we can either dilute a solution and make it less concentrated, or we can concentrate a solution and add more solute to the system. So now we're going to talk a little bit about formation of solutions. So formation of a solution is an example of a spontaneous process, and a spontaneous process is going to be one that does not require energy from an external source. And the two ways that a formation of a solution is going to be spontaneous is based on a decrease in the internal energy of a system, right? So this is an exothermic process. It releases energy, and this is not always going to occur, right? So oftentimes the formation of a solution is an exothermic process, but that doesn't always happen. But what does always happen is that you have an increase in the dispersal matter of a system. So we call this an increase in entropy, right? So an increase in the disorder of the system. So when we form a solution, we're always going to have an increase in the disorder, but we won't always have a decrease in the internal energy. And one example of this is an ideal solution. So an ideal solution is going to be when the strength of intermolecular forces between the solute and the solvent are no different than the solute-solute or the solvent-solvent forces. Okay, so when this happens, there's no energy change. It's not considered exothermic or endothermic. And an example of this would be a mixture of ideal gases. So in the picture below, we have helium on the left, which is separated from argon on the right. And then when we open this valve in the center, we're going to mix those two gases together. But because there's no difference in the interactions, because both of these only have dispersion forces, they're both considered noble gases. So we're not going to have a decrease in the internal energy. So not considered exothermic here. But we do have an increase in the disorder. And that is because now helium and argon can both occupy larger volumes. And so we do have an increase in entropy of the system. This can also happen if you have structurally similar liquids. So if you have something like pentane and hexane that are mixing together, they are both considered hydrocarbons, similar chain length, and so those would also be considered an ideal solution, and so not exothermic or endothermic. Now, when we look in detail at the formation of a solution, you're going to have three different types of attractive forces. There's the solute-solute and the solvent-solvent. Now, these two types of interactions, they're what kind of start out before the solution is formed, and so we need to overcome those solute-solute attractions to separate that solute out. And we also need to overcome the solvent-solvent attractions to separate those out, right? So this is step one here where we can see that solute, we're trying to separate the particles between them. And then step two here, again, you're trying to separate out that solvent. So those are considered endothermic processes. They require energy to overcome those attractions. And then the exothermic process, that's going to be when we form the new solute-solvent attractions. And so this right here, this is step three. That's what we call solvation. So the magnitude of energy for each of the three types of attractive forces, those are going to help us determine whether an overall formation of a solution is exothermic or endothermic. So remember, endothermic solutions are going to be when you have stronger solute-solute and solvent-solvent attractions, and you would have weaker solute-solvent attractions, right? So the endothermic processes would be larger than the exothermic processes. Now, if those endothermic processes are too strong, if there's too much energy required to overcome them, then you may not have a solution form at all, right? So if the energy required is significantly greater than the energy released, then you're not going to have a solution form. Now, the opposite, if you have very strong solute-solvent attractions and weaker solute-solute or solvent-solvent attractions, then you'll have an exothermic solution, right? So just keep in mind, exothermic will have stronger solute-solvent attractions. Endothermic will have stronger solute-solute or solvent-solvent. And so exothermic would have stronger solute solvent. Okay. So we're going to now jump into a topic on electrolytes. And in order to do this, you'll probably want to go back and review your acids and bases from Gen Chem 1, review how to name them, right? Whether you include that hydro prefix for your acids and what the different types of endings are. You've got the IC ending versus, oh goodness. There we go. IC endings versus, sorry, maybe I shouldn't write up there. IC versus OUS endings for your acids. Okay, so we have 7 strong acids that we need to memorize. The first 3 are going to come from your halogens, your chlorine, bromine, and iodine. So that's hydrochloric, hydrobromic, and hydroiodic. The one halogen that's not listed there is hydrofluoric, and that's considered a weak acid. Then you also have nitric acid, HNO3, sulfuric acid, H2SO4, and then perchloric and chloric acid. Okay, you want to consider all other acids to be weak, and remember that if you're trying to determine if something is an acid and you're not given the name, you're just given the formula, remember that most acids are going to start with 1 or more hydrogens. So all of those 7 strong acids, you can see that the hydrogen is listed first, or you may have 2 or even 3 hydrogens listed. Some exceptions to this that are still considered weak acids, but the hydrogen is not listed first, would be your carboxylic acids. Okay, so these are your organic compounds. And they're going to end with COOH or CO2H. And an example of this is acetic acid. So you saw acetic acid in Gen Chem 1, I'm sure several times. It's the compound that's in vinegar. And sometimes you'll see it listed, this first formula, CH3COOH, or sometimes they'll put that hydrogen first, HC2H3O2. So of course the second formula, it would be obvious that it's an acid, but it's not always going to be pictured that way. And ammonium is another type of weak acid. It is the conjugate acid to ammonia, which is a weak base. So, in addition to your acids, we have 6 strong bases that you're going to want to memorize. I think those are easier because they are all alkali and alkaline metal hydroxides. So remember, your alkali and alkaline metals are your first 2 groups in the periodic table. So I have those pictured here on the right. And as you go down, you've got lithium, sodium, and potassium. And then you stair-step over to calcium, strontium, and barium. Okay, so those are your 6 metals that are going to form with the hydroxide to give you a strong base. So you want to consider all other bases to be weak. Remember that most bases are going to contain that hydroxide ion, and you do want to keep in mind that that is different than an alcohol group like what you see up here with your carboxylic acids, right? So remember that the hydroxide ion is going to be bonded to a metal. Right? If we see an OH group that's bonded to a nonmetal like an oxygen or a carbon, then those are going to be alcohol groups, which are separate from your hydroxide ion. And then some other exceptions to the rule that are weak bases are your amine groups. Again, these are your organic compounds. Ammonia is the most common. You've got methylamine, which is CH3NH2. And basically you could increase the number of carbons attached to that nitrogen or attached to the carbon. So we could increase the chain length and say CH3, CH2, and then NH2. That's still considered a weak base. Or you could start attaching to that nitrogen carbons on either side and still have that weak base, okay? So any amine is going to have a hydrocarbon, typically with a nitrogen attached in there somewhere. Okay, when we're comparing the strong versus weak versus non-electrolytes, so keep in mind that we're talking about disassociating. So we're talking about breaking apart into ions. We are not talking about dissolving, right? Dissolving is about dispersing through the solution, right? It's solubility in water compared to disassociate, that's breaking apart. So strong electrolytes, they will fully break apart into their ions. Some examples of strong electrolytes are going to be any of your ionic compounds. Of course, remember those are going to be your metals that are attached to nonmetals like sodium chloride, table salt, and any of your strong acids or bases. And then your weak electrolytes, those will partially disassociate into water. And those are going to be your weak acids and weak bases. So remember, these are going to be your carboxylic acids, your amines, and anything that's not one of those 7 strong acids or 6 strong bases. And then a non-electrolyte that's not going to disassociate in water at all. So examples of these are going to be your sugars, right? And remember, sugar compounds, they're going to contain some number of carbon, twice the number of hydrogens most of the time, and the same number of oxygens as they have carbons. So you'll have some combination of C, H, and O. And then also your alcohols. Remember, your alcohols are going to be separate than your carboxylic acids. So ethanol is an example of an alcohol. That's where we have CH3, CH2OH. Okay, so alcohol is just an OH group. A carboxylic acid, which is a weak acid, remember that's going to contain 2 oxygens side by side and then that hydrogen on the end. So ionic electrolytes, again, just review from what we've already talked about. They are going to disassociate, which means that they will separate into their ions. And the intermolecular force that is going to be between the solute and the solvent are our ion dipole attractions, right? So remember that water is considered polar. And so if we have a water molecule here, just remember that oxygen is partially negative and those hydrogen atoms are partially positive. And so we can see that the hydrogen atoms pictured are attracted to the negatively charged anion, which is that chloride ion. And then the oxygens, which are partially negative, those are going to be attracted to your cations. Okay, and just keep in mind that ionic compounds, those are strong electrolytes, even if they are only slightly soluble. So if you look at your solubility rules and you find that an ion is just slightly soluble in water, it's still considered a strong electrolyte because the small amount that does dissolve will disassociate completely. Okay, so even if it's not very soluble, it will still be considered a strong electrolyte. Okay, and just the last slide here, covalent electrolytes, we've talked about this. Those are going to be your strong acids and strong bases will be your strong electrolytes. Weak acids and weak bases will be your weak electrolytes. Okay, so as an example, we have hydrochloric acid dissolved in water. So pure water or pure hydrochloric acid, those are not going to be considered electrolytes. They don't break apart into their ions. But when you mix them together, because hydrochloric acid is a strong acid, those like to donate protons, donate hydrogens, and so a hydrogen from that hydrochloric will be donated to the water. And when that happens, you form the hydronium ion, which is H3O+. Okay, and then that chloride ion. Okay, so then it does become ionized and you do have a strong electrolyte. So that ends this section on the introduction of solutions.